doing the problem. Okay, just noodle power here. So find the radius that would maximize or minimize the total surface area, including the top and the bottom, on a cylinder. Assume a fixed volume of 100 milliliters. That's all you would be given on a typical problem. So you say, all right, we've got a cylinder. So you start drawing your cylinder. There's my cylinder. And I want to read the problem. I want to read the problem and minimize or maximize what? So I read the problem. Minimize the total surface area. That's it. Minimize. Step 1. Minimize surface area. I'm just going to use area, or A. That's what I've got to minimize. Second step. Read the problem. Second step. Figure out a formula for whatever it is that you're trying to optimize. So I need a formula for area of the cylinder. Let me see. For the area, I'm going to need this letter R. I'm going to need the H, which would be the height. And that's it. The area is equal to pi r squared on the top, another pi r squared on the bottom, so that's two of them, plus 2 pi r times h on the sides. That's the whole side around, all the way around. So check, I got a formula. On such formula, eliminate all but one variables. What does that mean? Well, that's the one step where we have to eliminate the h. You see, I have a that depends on two variables now, r's and h's. I can't have that. If I want to plot this on an axis, this is going to be my a. I can't have two different variables for the bottom one. I either have r or I have h, but I don't want to have r's and h's, because that would turn it into a third-dimensional problem, which we're not ready for. You'd have to pay extra money for that. To just keep it two-dimensional, you got to eliminate one or eliminate the other. Capiche? How are we going to do that? That would be the third step, right? Let's go with white. Third step, eliminate all but one variable. So we had this idea that the key here, you got to read the problem. There's hints in there about it. Fixed volume is 100 milliliters. That right there, that's the hint to tell you how you can eliminate one of them, because volume is equal to pi r squared h on a cylinder, and we said it's 100. So 100 divided by pi r squared, that's equal to h. So this gives me an exchange rate. Every single time I see an h, I can exchange it for 100 over pi r squared. I see an h there that I don't like. I want to exchange that for r's. So I have my area is equal to 2 pi r squared plus 2 pi r. Instead of the h, I go with 100 over pi r squared. And look at my scan through my formula now. Area is expressed in terms of just one variable, r. In fact, I could clean it up a little bit. 2 pi r squared. The pi's cancel. One of the r's cancels. The 2 times that gives you 200. 200 over r. Alright, and look how beautiful that area is. You like it? Yeah, I like it too. That's the third step. Read the problem. Maximize or minimize what? Figure out a formula for what? Check. Eliminate all the variables but one? Check. You'll always have a hint. If you read the problem, if you think about it enough, you always have a hint that'll help you eliminate all the variables except one of them. Now we're in business. All we do is look for critical points. That hint right there, that if it's a critical point, the derivative must be 0, that's Fermat's theorem. It says, hey, if you got a max here, the derivative must be 0. It's flat. It's common sense. But I guess no one had common sense before Fermat, because he's the one that named, or he's the one that's named, the theorem is named after. Fermat's theorem says, if you've got a max, your tangent slope must be 0. A beautiful idea. It's so simple and elegant, and that tells you exactly what it is. So we're going to look for critical points now. Let's do it. Talk is cheap. So I know I got to find AR now, the derivative with respect to R. So that would be 2 pi r. That would give you 4 pi r plus 200 times the derivative of 1 over r. What is the derivative of 1 over r? Well, for that, you got to think about it as r to the negative 1. That would give you negative 200 times r to the negative 2 using power rule. So when it's all said and done, the derivative is equal to 4 pi r plus negative 200 all over r squared. This is a negative, right? And that's my derivative. I set it equal to 0, or I find places where it doesn't exist. When r is equal to 0, I got discontinuities, but r is equal to 0 wouldn't have much meaning in my problem. If my can has radius 0, then I don't have much of a can. So I'll forget about that one. I'll try to find the other critical point. I'll set it equal to 0, so that gives me that 4 pi r is equal to 200 over r squared. So r to the third times 4 pi is equal to 200. By the way, I moved this to the other side. This to the other side. That's how I got to this point. Then I could do r to the third is equal to 200 divided by 4 pi. Then that gives me r is approximately, this has 3 solutions, but 2 of them are not real, so the only real one would be the cubic root of 200 over 4 pi. That's it. All I gotta do is put that on my little magic number machine, and I'm set. You guys want to try it? Let's try it. Let's open up our parentheses here. Let's clear everything. Let's open up our parentheses and let's go with 2. So I think I got it in there. 200 to the 1/3 divided by 4 pi to the 1/3, and get my little magic machine, and there it is. R is 2.5154. What in the world did we just figure out? We found out that if your radius is 2.5154 centimeters, you've got a critical point, which means what? Right here, that number should be 2.5154. At that point, your tangent slope is 0. Now, based on the picture and based on our little experiments before, that should be a minimum. But how would you check that carefully? Well, you got 2 options. Either check the second derivative and make sure it's concave up, and that would do it. That would resolve it definitively. If it's concave up and the first derivative is 0, it's got to be a relative min. The other option is to check the first derivative, study the first derivative, and make sure that here it's going down, 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 down. That means it's going down. And afterwards it's going up, 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 up. That would definitively tell you that it had to be a minimum, because it went down, and at that point it went up, and at that point the derivative was 0. Those are the 2 options to check whether or not we have a min or max. And I'll let you check those. Those are pretty easy to check. In fact, the result you'll get is that in fact it is a minimum. And so we looked for critical points, we found them, test it to a critical point, and you're set. You've got yourself a minimum. And so you can go back to your spreadsheet and we can actually calculate 2.5. So if let me make it even bigger. If I make I'll make this one smaller. This one doesn't matter that much. These are my only columns that I'm interested in. The radius and what the surface area is. But if I make my radius 2.5154, there's nothing better than that. That is well, I round it off, but that's the optimal surface area. There's no other number that I can choose that will give me a lower surface area than that. That was nice. That's elegant. It was a simple idea. Find the places where the derivative is 0, and you're done. Okay. Now let's do some more classical problems. Here's how it would go. Typical problem from a typical textbook. Find the largest possible area of a rectangle that can be inscribed inside a circle of radius 5. What that means is that you could describe this type of rectangle, or you could maybe make it a little thinner so you can gain some height. But if you gain some height, you have to give up some width, and there's a debate on whether or not this would have more area or that one. Maybe this one has more area, but if flatter is better, maybe you can make it even flatter. But if that's better, maybe you can even make it flatter. But every time you make it flatter, you give up some height. So among all the possible rectangles that can be inscribed in a circle with radius 5, which one would have the largest area? That's the problem right there. Okay? It might seem daunting, but if you follow our little recipe here, it's actually pretty doable. We read the problem and read the problem until we figure out what are we trying to optimize. So find the largest possible area. So first step, optimize what? area. First step, area. I'm after area. Okay, area. Second step, find a formula for area. If you want to find optimized area, you can't go anywhere if you don't have a formula. Area of what? Area of the circle? No. Area of the rectangle? Yes. So the area of rectangle. When you do that, you gotta give it some name. So I'm just gonna call this one X. I'm gonna call this one Y. So then the area of the rectangle would be, well, I could make this one Y as well, right? And this one would be X. So this little square would be XY. But I have 4 of them. 1, 2, 3, 4. So I could say 4 XYs. There's a formula for it. Or you could think about it this way. This one is 2Y and this one is 2X. So the area would be 2Y times 2X, which is 4XY. Told you. Whatever. I found the area. Third step, eliminate all but one variable. See, I got too many variables here. I got X's and Y's. If I plot my graph here with A here and X's and Y's, it's going to be a mess. I'm going to have the bottom be two-dimensional, and you haven't paid enough money for that yet. So I don't want Y's or I don't want the X's. I only want one variable. There's always hints inside the problem that tell you how to do that. This one tells me that the radius is 5. So this is 5. This is Y. Here's the hint. X squared plus Y squared is equal to 25 by Pythagoras. So therefore, Y must be equal to the square root of 25 minus X squared, just by using Pythagoras. So my area is equal to 4 times X times 25 minus X squared. Told you. That's the third step. What was the third step? Eliminate all but one variables. Check. Fourth, look for critical points. Well, now I'm in business. All I got to do is figure out critical points for that. I can imagine, by this time I can imagine a formula with A and X's, and you know, maybe it looks like this or whatever. All I gotta do is find the maximum point there, and that is so easy to do because I'm gonna look for points where the derivative is 0. I may get other points where you have this I may get other critical points, but I'll test it. I'll make sure that it's concave down, or I'll make sure that it's increasing and then decreasing using my first derivative ideas. Okay, we're almost there. See, this one took us a whole 20 seconds to do. That's how long they should usually take. Alright, let's do it. Talk is cheap. I got 4x, 25 minus x squared. Oh, I think I forgot the square root, right? Nobody said anything. What, do you guys sleep or what? Square root of 25 minus x squared. Let's do it. So if I have f of x, which is equal to 4x times 25 minus x squared to the 1/2, how do you find the derivative? Well, you got to do a product rule here. Alright, so let's take the derivative of this guy, and we'll do it very carefully. F prime of x will be the derivative of the first times the second plus the first times the derivative of the second. The derivative of the second will be 1/2 25 minus x squared to the negative 1/2, because I subtract 1, and then I do derivative of the stuff inside, which will negative 2x. I clean it up a little bit. That would be 4 times 25 minus x squared square root plus, I got a 2 and a 2 and a 4. What's going on here? The 2 and the 2 cancel, so all I have is a negative 4x squared. And then I put this on the bottom because that exponent is negative, so it gives me 25 minus x squared. And I set that equal to 0. Okay, find places where the derivative does not exist, or where it's equal to 0. It doesn't exist if x is equal to 5, but that's not that meaningful, because if x is equal to 5, x would have to go all the way over here. That would give me actually the minimum area of a rectangle. In fact, it wouldn't be much of a rectangle if x stretched all the way to 5, to the radius of the circle. So that won't be as interesting. I want to find other critical points, and so I move this, set it equal to 0, move that to the other side. That gives me 4 square root of 25 minus x squared is equal to 4x squared all over the square root of 25 minus x squared. I can multiply both sides by that, maybe cancel the 4's. That gives me that 25 minus x squared is equal to x squared, or that 2x squared is equal to 25, or that 12.5 is equal to x squared, or that x is equal to plus or minus the square root of 12.5. That would give me a total of, how much is Let's clear everything. The square root of 12.5. It's about 3.53. Okay, 3.53. And what that does for us, what does that do for us? It tells you that when x is 3 point whatever that was. Whoa, what happened to it? Did I erase it? Square root of 12.5. 3.53, I'll say 3.54. 3.54, when x is 3.54, I have a critical point. Now I want that to be largest, I want that to be a max. So if I was imagining a 3.54 being the maximum area, I would want this to be concave down. Okay, either that, or I want it, the first derivative, I'll check the first derivative, it should be plus 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 on the left, and it should be minus minus minus. That way I knew it was going up and then it was going down. That's the fifth step, testing it. And so we test it. Let me think, we test it. Let's test it. Let's test it here. This is the derivative. 3.5 whatever. F prime of x. Let's choose something to the left of it, like 1. If x is 1, this gives you positive about 4 times 5. This gives you negative 4 divided by, this gives you something really, really smaller than 1. This gives you something that's approximately 4 times 5. It's going to be positive. Check it to the right. It's going to be negative. I told you. This is going to be a max. And so that tells you that this is a relative max. And that's it. This gives you the optimal shape. You take this 3.5 and you can plug it into this x and get exactly what the maximum area is. It would be 4 times 3.54 times the square root of 25 minus, no, let's clear that. 25 minus 3.54 square. Okay, close the parentheses. Bam, right there. That's the largest possible area. 50. The maximum area that you can inscribe a circle. The maximum area of a rectangle inscribed in a circle of radius 5 is 50. Following the recipe. Boom, 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 boom. Told you.